Well, in this third video, we'll talk about integrating processes and IMC tuning, so a way of tuning a PID controller for this type of integrating process. Section 5 is about space vector transformations, and section 6 is about phase lock loops. And at the end of that, we'll be ready to do your second exercise. So an integrating process is an accumulation process. What you see here is a water tank where you have kind of an actuator which is a valve, and using this valve you can adapt the input flow. Okay, there is also an output flow, and well, the variable that is going to be controlled here is the level. Okay, and this is going to be my process value. Okay, my level is constructed from the difference f in minus f out that is being integrated. Okay, so a water tank is actually an integrating process, and you see the analogy here with the DC bus. Okay, well, you replace your water tank by a capacitor. Okay, and the voltage will replace the L. Okay, the flow will be replaced by a current, an input current in this case, and the output flow will be replaced by an output current. Very different processes, but same behavior in terms of the model, and also same kind of tuning for the controller parameters, as we'll see later. Well, we'll look at the behavior of this integrating process. In our case, it's a water tank, and you see that in the original valve position the level is decreasing. This means that in this case the output flow must be larger than the input flow. Okay, so the input flow is influenced by the valve position over here. Here the valve position is changed, and suddenly you see that the level is increasing. So in this case, f in, the input flow must be larger than the output flow. The only instance where the level is constant is when both f in and f out are exactly equal. Well, an integrated process is very easy to describe in the time domain. Okay, so you take the input and you integrate it over time, and there is also one parameter which is the gain of the integrator process. Sometimes, for instance, in a PI controller, the gain is written as 1 over a time constant, the time constant of the integrator. When you go to the Laplace domain, okay, the equation of the integrator is simply written like that. Well, integrating processes are very easy to model, and this is particularly true for our two electrical examples here. Well, if you look in the Laplace domain, you know that the voltage is 1 over Cs, and the input is the current. Okay, so this is the relation. Okay, so this gain Kp over here, it's simply 1 over the capacity. If you're looking at the current that is flowing through a capacitor and its influence on voltage, and you have something similar here for an inductor, the output current is 1 over Ls, and you take the input voltage. Okay, so in here the gain is Kp is 1 over the inductance. Well, this is the body diagram of the integrating process. Remember that you replace S by J omega. Okay, then you compute the module, and then you compute the argument. And if you do that, you will see that the module will be decreasing with frequency, okay, and so you have a slope of minus 20 dBs per decade, and you will see that the argument, okay, because you have 1 over j omega, is minus 90 degrees, but this is something that you've seen in other courses. Well, in reality, control loops that involve an integrating process are often not well optimized. This is strange because they are actually quite easy to optimize if you use these IMC tuning rules, okay, and they will be derived here for the integrating process, okay. So this is the process that we've introduced before. We'll use a PI structure. It would be nonsense to use a PID structure, so D action is never used on an integrating process. The PI controller structure can be written like this or like this, okay. So if you write P over S times C over S, you can kind of see that the closed loop transfer function, okay, this is the closed loop transfer function from set point to controlled process variable, is like this. And if you look at this product over here, P is here, C is here, you can see that this denominator will be of the second order. So there will be two poles in the closed loop transfer function. And what we'll do is make sure that these two poles are placed at this quantity here, okay. So we'll put them somewhere over here in minus TCLP. Well, we need to put them to the left of the imaginary axis to make sure that the closed loop is stable. And this TCLP will actually be our design parameter, okay. It is the desired closed loop time constant that we need for our control loop. Since we have a second order, we need to impose both poles at this location. So this is imposing that the denominator of my transfer function will look like this, and this you can expand to what is written over here. Well, remember that the closed loop transfer function was PC over 1 plus PC, and that P of S, because I should add an argument S over here, is equal to KP over S, and that the PI controller is equal to KC, the gain of the controller, times okay. So this thing here can be constructed from these two quantities, and if you do the calculation, you will see that the closed loop transfer function is like this, and indeed you see that the denominator is of the second order, okay. This is this denominator, and this has to be equated to what we had decided before, okay. This is to impose two poles, P1, 2, equal to minus 1 over TCLP, and this parameter is going to be our design parameter. This is the closed loop constant, the desired closed loop constant that we need for our for instance current loop or voltage loop, or in our PLL, because this IMC tuning will be using it 3 times. So if we equate this thing here and this thing here, so if you impose that they are equal, you can kind of see very easily that this is your integration time constant, this is TE, this is what you see over here. I should write it like that, okay. And then you have that this thing here is 2 times TCLP, okay? You equate this thing here with this thing here, and you see that the gain of your controller is given by this quantity over here, okay? Kp is the gain of your integrating system, you know, and as I said, TCLP is your design parameter. It's the desired time constant in closed loop. So you can kind of show that if you use IMC tuning, the response will be something like that. And in order to show you, I need to return to the previous slides. Okay, so this is your closed loop transfer function. The numerator is this thing here that you've seen in the next slide, and this thing has been equated to TCLPS plus 1, the whole thing squared. So indeed we see that the response is given by this quantity over here, okay? And you see that with IMC tuning, the integrating time constant is 2 times TCLP. If you plug that in here, you can kind of see the response. Okay, so that you can split in a lead lag part and a first order part. Okay, so the response to the lead lag part you can see here in green. Okay, you can kind of see that this is correct because at time instant t equals 0, you have to look at what's happening when s is going to infinity. Okay, so you have to take the initial value theorem. We assume that we have at the input here a set point that is going to move as a step, so the 1 over s and the s of the initial value theorem are going to cancel. Okay, so when s is going to go to infinity, you see indeed that you'll have a response at 2 when t equals 0, and when t is approaching infinity, so at steady state, you have to look at what's happening when s is equal to 0, and there indeed you see that the gain is 1. Okay, so this is the response of the lead lag part, but of course there is an other part here. If you now combine the lead lag part in green, and if you kind of think that this green curve goes through a first order, well, you can kind of imagine that the response of your integrating system with the IMC tuning parameters, well, the response will look like this curve over here. Okay, and this is TCLP. So in 1 times the desired closed loop time constant, well, you arrive at the set point. There will be a little bit of overshoot and then it will come back. Of course, there's something that is not shown over here. It's the quantity mv, the manipulated value. Okay, if you choose TCLP too small, this will of course have an influence on the manipulated value, in the sense that your controller is going to react too aggressively. So this has to be chosen with care. Section 5 is about space vector transformations, and we'll talk about the Concordia and Clarke transformations, and then about the Park transformation. Well, you're familiar with the ABC framework. The 3 phases, A, B, and C, are shifted by 120 degrees, as you can see. At any given time instant, the sum of all the 3 phases, which is also called the homopolar component, is 0. And this is always the case when the system is balanced. As you can see, the 3 phases can be constructed from a rotating vector. This rotating vector is projected on 3 axes that are 120 degrees apart. Well, the three axes that are 120 degrees apart are here. So this is the first one related to phase A. Here is the second one related to phase B, and here is the third one related to phase C. Well, you can see indeed that the rotating vector in black is being projected on the a-axis, okay, and then a factor 2/3 is applied, and so you obtain this vector over here, okay, and you can find it back over here, okay. You have something similar with the projection on the b-axis. Okay, here's the projection. The factor 2/3 is being applied, and you obtain the component for the phase B. And of course, you can do something similar for the third phase C. So you project on the C axis and you apply this factor 2/3, and this is what you obtain. Okay, so this is the component for the C axis. So you can see that at all times the rotating vector in black is decomposed as the sum of its projection on the A axis plus its projection on the blue axis, okay, B axis, it's this vector over here, plus its projection on the C axis, okay, this is this vector over here. Well, we have seen that in the ABC framework the signals are shifted by 120 degrees. There is information about amplitude, phase and common mode, but it's kind of mixed, right? So this is the motivation for the Concordia and Clarke transformations, and they will transform the ABC signals in three signals, alpha, beta and the homopolar components. The two first signals over here are two signals that are in quadrature. This means that they are shifted by 90 degrees, and these signals will contain information about the amplitude and the phase, okay, and this third component will be the homopolar component, which is the sum of all the three phases. So we can see that using these transformations the information is decoupled. Amplitude and phase information is contained in the two first signals, these alpha beta signals that are shifted by 90 degrees, and the common mode information is contained in this homopolar component. In our application, well, the homopolar component will be 0 because the signals will be, well, balanced, okay, so we can forget about these homopolar component and just use the alpha beta signals. Well, in order to transform the signals from the ABC framework to the alpha beta 0 framework, you need to use the Concordia transformation, okay, this is this matrix over here, and we'll denote it like that for short. And of course you have an inverse transformation that transforms the signals alpha beta 0 back to the signals in the ABC framework, okay, and you need to use the inverse of this particular matrix. So this is this inverse, okay. If you look closely, you will see that this inverse matrix is simply the transpose of this one. So this means that this transformation matrix is orthogonal, okay. Why is that? Well, you know from the course on linear algebra that if the inverse is equal to the transpose, well, your matrix must be orthogonal. In the literature, you will find a transformation that is closely related to the Concordia transformation, and it's called the Clarke transformation. Later on in the course, we'll show you why there are two transformations. Okay, so this Clarke transformation is very similar, as I said, and the only difference comes from this term over here. And in the Concordia transformation, this term is replaced by the square root of 2/3. Okay, so this change, okay, of the factor from square root of 2/3 to 2/3 implies that the inverse transformation is obtained like that, and as you can see, it is not the transpose anymore. So this transformation, this Clarke transformation matrix, is not orthogonal. Well, you see that using this Clarke transformation and forgetting about the homopolar component, we are left with the two signals alpha, beta, and instead of projecting the rotating vector on three axes that are 120 degrees apart, we're projecting on two axes, this one and this one over here, that are 90 degrees apart, and this is how the alpha beta signals are obtained. Well, let us now take a three-phase signal which has amplitude xm, and as you can see, the three phases are 120 degrees apart from one another, and then we apply the Concordia transformation to this signal, okay, and the Clarke transformation to this signal. This is something that, for instance, you can do using the symbolic toolbox of Matlab, and what you will obtain, of course, are alpha, beta, and the homopolar component, okay, and this homopolar component over here is 0 because we have a balanced signal, and we have indeed two signals that are 90 degrees apart from one another, a cosine and a sine, and the difference between the Concordia transformation and the Clarke transformation is in the amplitude. Okay, you see that with the Concordia transformation, the amplitude of the original signal is not preserved, whereas in the Clarke transformation, you can see that indeed it is preserved. So you can say that the Clarke transformation is amplitude invariant. Well, what we'll do here is compare the three-phase power and the power that you have after transformation and compare these. Okay, so you know that the three-phase power, it's the product of voltage and current element by element, and then you sum them, and one way of writing this is to write it like this. Okay, so you can see this as a scalar product. Okay, so what we'll do is write the vector that we have over here as a function of the voltage, but after transformation. This can be done using the inverse transformation, okay, and we'll do this for the Concordia transformation and for the Clarke transformation. You know from the course of linear algebra that A times B transposed is B transpose A transposed. Okay, so you have a transposed over here, so you can rewrite what you have got over here to this thing here. Okay, so what we'll have to do is compute this thing here for both the Concordia transformation and for the Clarke transformation. So we'll have the relation between power, three-phase power before transformation in the ABC framework, and then power after transformation to the alpha beta homopolar component framework. Okay, so this computation you can do again using the symbolic toolbox of Matlab. Well, if you do this calculation here for the Concordia transformation and for the Clarke transformation, this is what you obtain. So for the Concordia transformation, you have a identity matrix, which gives you a relation between the three-phase power and the power after transformation. Well, very often we'll have a balanced system, so we can kind of forget this term over here. So we see that the power after transformation by the Concordia transformation is preserved. For the Clarke transformation, well, the relation is a little bit more complicated. So if we assume that our system is balanced, okay, then you can see that the power using this Clarke transformation is not preserved. Okay, so we arrive at the conclusion that the Concordia transformation is power invariant, and we had seen that the Clarke transformation is amplitude invariant. Well, we'll be working with balanced systems, so the advantage of these two transformations is that a three-phase system becomes a two-phase system where the two phases are in quadrature. This means that the two phases are shifted by 90 degrees, and we get rid of the redundant information because in a balanced system the homopolar component is always 0. So we'll only use these alpha beta signals, and instead of using 3 controllers, we can work with only 2 controllers. Well, we have seen that for balanced systems this homopolar component does not give additional information, so it's kind of redundant because the homopolar component is simply always 0. So we'll use a reduced transformation matrix, which is defined as follows, and the matrix is then a 2 by 3 matrix. And you have something similar for the inverse Concordia matrix. You can reduce it to a 3 by 2 matrix. And of course you have something similar for the Clarke transformation. We're going to introduce a new transformation, which is the Park transformation, and the motivation for this transformation is that we know that all the signals we're working with are sinusoidal. So we would like a transformation that will transform the signals into signals that are fixed in time, okay, so time invariant or slowly time varying if the signals are not perfectly sinusoidal. And the motivation for that is that we would have controllers that can settle out, and you will see also that with this transformation it's easy to extrapolate a signal. For instance, when you have a sinusoidal signal, if you have to kind of see what will happen in the future, it's difficult, but with this Park transformation this will become easier. Well, the Park transformation transforms the signals in the alpha beta framework to the so-called DQ framework, and this is done by using a reference frame that you see over here, D with a D axis and a Q axis that is perpendicular, and this reference frame is rotating at the same speed as the rotating vector. So from the perspective of this rotating frame, everything looks fixed, and then simply the rotating vector is expressed in this rotating frame. So you have a D component and a Q component. Let's look to the animation, and you see that indeed, as the frame is rotating at the same speed as the rotating vector, everything looks fixed in this rotating frame. Well, with the Park transformation, the rotating components in a fixed reference frame, which is the alpha beta frame, are transformed in fixed components in the rotating frame, which has components D and Q. Well, you can see that the rotating vector here in purple and the DQ rotating framework are rotating at the same speed omega. Okay, the reference angle is different. So the reference angle of the rotating vector is theta, and the reference angle of the dq framework here is theta ref, and this theta ref is problem dependent. The d component is in phase with the reference signal, okay, and the q component is in quadrature with the reference signal. So for instance here, if theta ref and theta would be equal, okay, then you would have only a d axis component which is in phase with the reference signal, and there would be no q axis component. So remember that we had started from an A, B, C framework where the axes were 120 degrees apart, and we've moved to this alpha beta framework where the axes here are 90 degrees apart, and you can either use Concordia or Clarke, and you know that Concordia is power invariant and Clarke is amplitude invariant. Okay, and we've seen that instead of working with this fixed frame alpha beta, you can work in a rotating frame dq. Okay, the angle between this rotating frame dq and the fixed alpha beta frame is theta ref over here, and you see that you can very easily go from this alpha beta framework to this dq framework by simply using a rotation matrix which uses this theta ref signal over here. So this slide kind of summarizes the transformations that we have seen. So at the top we have our ABC framework where the axes are 120 degrees apart and the rotating vector is projected on these three axes. And then we have seen, well, since we're working with balanced system, there is redundant information. So we decided to work in this alpha beta framework where the axes are now 90 degrees apart. So we work with axes that are in quadrature. Okay, so we are left with these alpha beta components, but you can see that the alpha beta components are still time varying. Okay, so we would like to have signals that are fixed in time so that we can use two controllers, but controllers that are going to settle out. And this is the idea of the Park transformation. The idea is simple. Instead of working with a fixed frame, we're going to use a frame in quadrature that is going to turn at the same speed of all the vectors in your problem, and in such a way they appear fixed in the rotating frame. So here we consider the Park transformation in steady state. So the Park transformation takes the three signals, or the three phases A, B, C in this fixed reference frame, and they transform it to the dq components, and there are two of them in this rotating frame. You know that of course there are these intermediate signals in the alpha beta framework, so you have first to do this transformation, which is here the Clarke transformation that is used, because you see that the signals are of the same amplitude, and then you go to the dq framework. So here it's this rotation matrix that is used, that we have introduced previously, and this is using this reference angle, and over here it's this matrix T Clarke that is used to go from the ABC framework to the alpha beta framework. Well, in this case we have a vector in purple and a reference frame in orange, and they are both turning at speed omega, the reference angle of the dq frame is theta ref, okay, and the reference angle of the vector is theta. So you can see that the difference between these two angles is phi over here. Okay, so this signal here is theta of t, and in this rotating dq frame, this vector appears as a vector of amplitude xm. Okay, this is because we had used this Clarke transform to go from the ABC framework to the alpha beta framework, and you see that the d component is this distance over here, okay, which is xm cos phi, and what you see over here, the q component is xm sine phi. Okay, this is indeed what you see over here. And indeed, if phi is equal to 0, then you'll have xd equals to xm and xq is equal to 0. So in that case, there is only a d component, okay, and if phi is equal to p over 2, you would have no d component, so it's 0, and xq would be indeed xm. xd is said to be the component that is in phase with the reference signal, okay, and xq is the signal that is in quadrature with respect to the reference signal. So here we'll consider an inductor and the relation between the voltage and the current in steady state after Park transformation. So what we see here on the left is that the reference angle for the Park transform is oriented along the reference angle of the current vector. So you have here theta is equal to theta ref, okay, so phi is equal to 0, okay, with phi defined as in the previous slide. So without a surprise, we have after Park transformation that we have only a d component in our current and that the q component is equal to 0. So we know that the relation between the voltage and the current is as follows, okay, so if we apply this, we obtain an expression of the voltage where the omega, of course, it's the time derivative of the reference angle. It's the speed at which this reference frame is rotating, okay, and this can be written a little bit differently as follows. So we can now look at the Park transform of this voltage signal, okay, and we see that this is here theta, so it's the reference angle of the voltage rotating vector, and it's shifted by p over 2 or 90 degrees. So this quantity here is my phi, and we have seen previously that if we take the Park transform with the reference angle theta ref, well, we'll have something that is along only the q component, and this is indeed what you have, okay. So you see that the current is along the d component and the voltage is around the q component. We will now look at the change in dynamic behavior due to the Park transformation. We had seen something quite similar in the course Dynamique des systèmes mécaniques. When you had a rotating frame, well, you had to take that into account, and we'll see something quite similar for the Park transformation. So what you see here is the Park transformation. You go from the alpha beta framework to the DQ framework, and for that you use this rotation matrix that you see over here, and we'll denote it like that for short. Let's now look at the dynamics after Park transformation. So we need to take the time derivative. This is what we obtain over here. So we need to take the time derivative on the right hand side, and here there are two components that are time dependent, so I expect two terms, and indeed this is what I see. So we'll take this one times the time derivative of these two signals. This gives you this first term over here, and now we have to take the time derivative of this one acting on these two signals. So what you see over here is indeed the time derivative of that. Okay, so you've got to take the derivative in chain, so the derivative of this rotation matrix with respect to the reference angle, this is what you see over here, times the time derivative now of the reference signal, and this is what you see over here. So we are going from this line to this line now, and for that we know that you can rewrite, for instance, this term over here using this relation. Okay, and you have something similar for V beta. Okay, so this explains this term over here. If you take the time derivative of the reference angle, this will produce the omega, and the omega is over here. And here I have simply introduced a identity matrix, okay, by simply saying, well, we are going to use this rotation matrix inverse times the rotation matrix itself. So I have not changed anything by introducing this identity matrix. So now I'm simply using my rotation matrix to transform here the voltage in the alpha beta framework to a voltage in the DQ framework, and we do something similar here but for the currents. Okay, so this is my current in the DQ framework, and this quantity over here, if you do the computation, it's not something that you'll do by hand, but you can use, as I will show in the next slide, Matlab for that, the symbolic toolbox. Well, if you do the computation, you can replace this quantity by this matrix over here, and you obtain this relation over here, and I will talk about the interpretation later. You can see that this expression was used in the previous slide, and it's something that you can compute quite easily using the symbolic toolbox. You have one variable that is theta, you write your rotation matrix, you take the derivative, and then you compute this quantity with this command. You just use the simplify command, and then you show that this quantity is simply this matrix over here. Well, this is the dynamics after Park transformation that we had obtained previously, and this equation you can rewrite it quite easily to this form. And in this equation, well, you can kind of recognize what you would expect, right? Is that the voltage is L times the derivative of the current, and this is indeed what you see with this term, but you see that there is an additional term, okay, and this additional term has to be added to take into account that you're working into a rotating frame, Okay, so this spark transform introduces this additional term, and you can see that it introduces a coupling effect. Okay, you can see that the voltage or the D component of the voltage depends on the D component of the current, but it also depends on the Q component of the current. Okay, so indeed the two differential equations are coupled. Well, we can now see if this equation is consistent with the steady state behavior that we had observed previously. And if we look at the steady state behavior, well, we can cross out this term over here, because in steady state we know that everything is constant. Okay, and we'll look at currents that are such that you have only this D component. Okay, so this means that the reference angle of the rotating frame is adjusted on the rotating current vector, and then we can compute what's happening, and you see that indeed you obtained what we had obtained previously. So the voltage is only oriented along the Q component, that is, there is no D component. In section 6 we're talking about phase lock loops. There are two methods, but we'll leave the first method aside, so it will not be covered in this series of videos, and I'll talk about the synchronous reference frame method. There is an analogy between a phase lock loop, or PLL, and racing cars. Well, there is a pace car that is driving in front. It has a certain rotational speed, and it's described by this rotation angle theta pc. And then there is the race car or chasing car, which has also a speed, and its position is described by the rotation angle theta rc. We'll assume here that the speed of the pace car is constant, and that the job of the race car or follower car is to lock on the pace car. Okay, so the distance between the two cars on the racetrack is simply the difference between the two rotation angles times the radius of the track. Okay, so if this distance is positive, okay, then the race car should increase its speed, and if it's negative, it should decrease its speed. Well, of course, if the distance between the two cars is 0, this means that the pace car is locked. Well, the race car should maintain its speed constant. Suppose this is our reference signal over here, and it's characterized by the reference angle theta ref that we want to track. So I'll draw my alpha beta here. And I have my reference signal that I want to track, and it's characterized by this angle theta ref. Okay, and then I have my angle that is produced by the phase lock loop. Okay, and this angle is the angle of rotation of my rotating reference frame, the Q over here, and this is my theta PLL. Okay, so the job of my phase lock loop is that this D component tracks my reference signal. Okay, so if we take the Park transform of my reference signal, okay, so I go from the ABC framework to dq framework using this theta PLL, you know that the result is going to be described like this. Okay, so this here will be cosine phi, and this will be sine phi, and phi is defined over here. So phi is theta ref minus theta PLL. Okay, so after Park transformation with my PLL angle, I obtain the following result over here. So I have a cosine of the difference and a sine of the difference. So if my PLL angle is close to my reference angle, I can kind of approximate this sine by what is inside of the sine, okay, which is only the difference between the two angles times the amplitude. And this looks a lot like we had before. Okay, it's the difference of the angles between the pace car and the race car times the radius of the track. Well, I now come back to my analogy. Okay, so the pace car is now the reference signal. Okay, and this reference signal is characterized by theta ref, and it has a constant speed omega ref. And the race car is the output of my PLL. It's going to be described by this angle theta PLL and by a speed omega PLL, and the job of the PLL is to track the reference signal just like it was the job of the racing car, okay, to track the pace car. And the idea is that, of course, you should work based on an error signal, and this error signal was simply the distance between the two cars. Okay, here we work with a racetrack that has a certain radius, okay, which is equal to this xm here, which is the amplitude of the reference signal times the difference between the two angles, the reference angle and the PLL angle. Okay, and we have seen previously that if the angles are sufficiently close, this looks like this signal over here, okay, where we have a sine, and this is the Q component of my reference signal after Park transform with the angle theta PLL. Okay, so the idea was to work with the error, okay, and if it's positive, to increase the speed of the racing car, in this case of the PLL, to increase omega PLL. But instead of working with this error signal, we'll work with xq, okay, the q component of the Park transform of the reference signal. And if it's negative, if the error is negative, or in our case if the q component is negative, well, we'll have to decrease the speed of our PLL. So based on this analogy, we can now write an algorithm for the phase lock loop, or PLL. So this is the signal we want to track. Okay, this signal has a certain reference angle, and we want our PLL to track this reference signal or angle. And we have seen that we are going to work based on an error signal, and this error signal is the Q component. Okay, after Park transformation of this reference signal using the PLL angle. Okay, and the idea was, well, if the error is positive, we need to increase the speed. If it's negative, we need to decrease the speed. And this we're going to do with a PI controller. Okay, so the PI controller is going to look at the error signal, XQ. Okay, and the goal of the PI controller is to make sure that this XQ component, which is a measure of the error, okay, is controlled to 0. So we'll use here a set point of 0. Okay, and the output of our controller will be, of course, the speed. Okay, and in order to go from speed to angular position, well, we need to use an integrator. Okay, so this is an integrator 1/s. Okay, so if you implement that, you have actually implemented a phase lock loop, and its job is to track the reference angle of this three-phase signal. Okay, so what remains to be done is to see how we can tune this one, and of course we'll use the IMC tuning that I've introduced previously. For that you need the description of the system. Well, the output of the controller is omega PLL, but of course that's the input of your process. Okay, you can see that you have an integration, so you have the 1/s. You have here a gain that is xm, okay, and here inside the controller you have a change of sign because of this minus sign over here. So the process is described by this integrating process, and so we have a process P of S is equal to Kp over S, and in our case Kp is equal to minus xm. Okay, so the IMC rules said that you should use Ti is 2 times the desired closed loop time constant, and in this case we'll call this desired closed loop time constant for the PLL TPLL. Okay, so this is indeed what you see over here, and you have that Kc is equal to 2 over Kp and TPLL. Okay, so if you inject this thing in here, okay, you indeed obtain the gain of your controller. Well, what has still to be determined is TPLL, so the desired closed loop time constant for the PLL algorithm. And you know that you're working with signals that are at 50 Hertz. So you have a period of 1/50. Okay. And you would like your PLL to track the reference signal as fast as possible. And roughly speaking, you can say that you would like your PLL to track the signal in 1/4 of a period. So you can approximately say that TPLL is 1/4 of 1/50. This is simply saying that in 1/4 of a period of 1 sign, you have tracked your reference signal. So you have everything that you need for your PI controller, and the only thing that you need also, but I assume that this is clear for you, xm, this is the amplitude of my grid signal. Okay, so it's 230 volts times the square root of 2, because you need, of course, the peak value. What we'll do now is use this PLL in our own application, and since we want to exchange power with the grid? Well, it's kind of natural that we are going to want to determine the reference angle of the grid, okay, and the grid voltage. See, so we are going to construct a block over here, which will be like this, and we'll call it PLL. And my signal here that I will be using at the input will be V grid A, B, C. Okay. At the output, what I will have is V grid D, Q. So it's the transformation of my grid voltage from the ABC framework to the DQ framework. And what I will have at the output also is the reference angle. I will call it reference angle, but because once my PLL extracts the reference angle, well, what I will observe over here is really the reference angle. Okay, so the output of the block in the next slide is indeed the reference angle, and what I can output also is the speed omega ref. Okay, here it says omega PLL, but again, once my PLL extracts the reference signal, what I will observe here is really the speed of my reference signal. Okay, so if we apply this to the grid voltage, of course this one should be very close to 2 pi times 50 radians per second. Okay, so what have we learned so far? Well, we're going to implement a PLL, and at the input of the PLL we'll put the grid voltage, and this is a signal with 3 elements, okay, because it's in the ABC framework. And inside this PLL block, well, you have to implement what's on the previous slide, and in that block you had a Park transform, you had a PI controller, and you also had an integrator. Okay, and this PLL, well, it gives the grid voltage in the DQ format. Okay, since it's in the DQ format, the vector should have 2 components. Okay, it will output the reference angle. Okay, so it's the output of my PLL angle, and it will output the rotation speed. So what you can do now that you have an estimation of your reference angle obtained by the PLL algorithm, well, you can take your other signals that are in the ABC framework, such as the inverter current, and transform it to the DQ format. We have already done that for the grid voltage, but you can also do this for the inverter currents, and therefore you have to use again this Park transformation. Okay, remember Park is Clarke or Concordia transformation followed by this rotation matrix, and you'll be using, of course, the estimated reference angle. So what we'll see later on in the course is that we'll of course compute the inverter voltage that is desired, and this inverter voltage will be in the DQ format. So it will be a 2-dimensional vector, and we'll use an inverse Park transform to produce the inverter voltage in the ABC format, and there will be a 3-dimensional vector, and of course you need a reference angle to do this inverse Park transformation. You could use the output of the PLL, but it's much better to use a prediction of this reference angle that takes into account the time delays that you have in every control loop, because you need to collect signals, because you need to compute your control algorithm. On the tri-phase system, this delay, this dt timing here, is 2 to 3 times the sampling period. Okay, so instead of using the output of my PLL when I do the inverse Park transformation, I would like to extrapolate things to take into account and to have a delay of 2 to 3 times TS. Okay, so I'm computing this theta ref here in the future, and I do this using this prediction block, and this is quite easy to do when I have done my Park transformation. So the prediction is simply the angle that you had, okay, plus dt timing times omega, and this gives you a prediction of the reference angle in advance. And what will be done is that this prediction angle will be used for the inverse Park transformation, and this will then take into account that your control loop has a certain delay.